Then let's review the increment relationship between loads and internal forces. Look at this example. If we take a differential segment dx around section B as this figure shown, the bending moment and shear force on left side of section B are MBL and FQBL. The bending moment and shear force on right side of section B are MBR and FQBR. According to equilibrium equation, FQB right is equal to FQB left minus FP. MB left is equal to MB right. The shear forces on right side and left side of section B are different, so the slope of bending moment diagram are different. The bending moment diagram has a sharp corner. If we take a differential segment dx around section C as this figure shown, the shear force on the left side of section C is equal to the shear force on the right side of section C. The bending moment on the right side of section C, MCR, is equal to the bending moment on the left side of section C, FCL, plus M. So, the bending moment diagram will have a jump on section C, and the value is equal to the moment acting on this section. The shear force diagram will have a jump on the section where a concentrated load acting. The jump value is equal to the value of the concentrated load. The bending moment diagram will have a sharp corner on this section where a concentrated load acting. Look at an example. That's easy for us to construct a bending moment diagram and shear force diagram. We could see that the bending moment diagram have a sharp corner on this section, and the shear force diagram will have a jump on this section where the concentrated load P acting. And the jump value is equal to positive half P plus half P, so that's the value of the concentrated load P. The bending moment diagram will have a jump on the section where a concentrated moment acting. The jump value is equal to the value of the moment. Moments will not influence the shear force diagram. Look at this example. That's easy to construct a bending moment diagram and shear force diagram. We could find that on this section, the bending moment will have a jump. The value is equal to M. And for the shear force diagram, it's a horizontal line. The moment will not influence the shear force diagram. The slope of this bending moment diagram of this part is half of L over half of L. That's M over L. The slope of this part's bending moment diagram is also half of M over half of L. So we find that actually these two bending moment diagrams are parallel. Just now we reviewed the differential relationship equations. If we do integral for both sides of the equation from section A to B, then we could establish that FQB is equal to FQA minus integral from A to B QY times dx. Here, this integral part represents the area of distribution loads for AB part. According to this differential relationship equation, we do integral for both sides from section A to B, we could also obtain that MB is equal to MA plus integral from A to B FQ dx. And this part, it represents the area of shear force diagram for AB part. These two equations represent the integral relationship between loads and internal forces. Now let's look at an example to see how to use the differential relationship, increment relationship, and integral relationship to construct internal forces diagrams of the structure. Firstly, let's draw the bending moment diagram. For BC part, Q is equal to 0. We know that the bending moment diagram should be a diagonal line. Section CM is equal to 0. For CB part, upper side in tension. For the right side of section B, M is equal to QA times A, that's QA squared. Now look at section B, because there is a moment acting on section B. According to equilibrium condition of the section B, we could draw section B's free body diagram as this figure shown. And according to equilibrium condition of section B, we'll know that for the left side of section B, its M is equal to 0. For the AB part, section A's M is also equal to 0 because no moment is acting on it. There's Q acting on AB part, so its bending moment diagram must be a parabola. We could determine that section D's M is equal to half of QA squared. Then let's draw the shear force diagram. For AB part, obviously its shear force diagram is a diagonal line because Q is a constant. We could construct its shear force diagram. For the AD part, that's positive. Section A's right side FQ is equal to QA. Section B's left side FQ is equal to negative QA. For the BC part, bending moment diagram is a diagonal line. According to the differential relationship, its shear force diagram must be a horizontal line. And the value FQ is equal to slope of the bending moment diagram, that's QA squared over A, so that's positive QA. After the construction of the bending moment diagram and shear force diagram, we could testify the result by using integral relationship. For AD part, FQD is equal to FQA, that's QA, minus the area of the uniformly distributed loads, that's Q times A, so FQD is equal to 0. For DB part, FQB is equal to FQD minus the area of the uniformly distributed load, QA, so that's 0 minus QA, that's negative QA. Look at the bending moment diagram. For section D, MD is equal to MA plus the area of the shear force diagram for the AD part. That's equal to the area of this triangle, positive half of QA times A, so that's half of QA squared. Summary. Today we reviewed the forms and calculation of single-span beams, and also we discussed the relationship between loads and internal forces. We reviewed the differential relationship, increment relationship, and integral relationship. These relationships are all useful to construct internal force diagrams. That's all for today. Thank you for your attention.